Hello. In this video we're going to look at finding the limit analytically, so algebraically, instead of using graphs or using a table. Both of those methods work if your number ends up being something that you can easily pick off a graph or easily recognize as a decimal. If not, then analytically is typically your best approach. Alright, so the first thing you always want to do is try to just plug in. Sometimes if you plug in, you get a real number and that's going to be your answer. And so we're going to try first to just plug in x equal 1. In this case, we're taking the limit as x approaches 1 of the function x squared plus 5x minus 6 over x squared minus 1. And if we plug in a 1 there, we're going to get 1 squared plus 5 times 1 minus 6 over 1 squared minus 1. And we see that this gives us 0 over 0. Well, 0 over 0 is what we call an indeterminate form. So an indeterminate form means that we can simplify. So anytime you see 0 over 0, that means simplify your argument, simplify that function. And so let's try. This is a rational function, and so the easiest way to simplify that is to see if there's any common factors. So let's factor the numerator and factor the denominator. X squared plus 5x minus 6 factors to x. Let's say they're going to have different signs. The biggest one's going to be positive, so plus 6 and x minus 1 are the factors of negative 6 that add to 5. In the denominator, we get x squared minus 1, and that is a difference of squares, so it's going to factor to x minus 1 times x plus 1. And we do see that we have a common factor of x minus 1. We can divide out on the top and bottom. And so we get that this limit is going to be the same as the limit of just the remaining terms. And now, when we plug in that x equal 1, we're going to get 1 plus 6 over 1 plus 1, and that does give us a real number. And so we get that this limit is equal to 7 over 2. So if we were to graph this and look at the graph as x is approaching 1 from the left and the right, both values would get closer to 7/2 or 3.5. All right, this next one's a little bit different because it's not a rational function. We have a square root in there, and anytime you see a square root, doesn't matter whether it's in the top like this or in the bottom that you saw in algebra, you really want to try to rationalize and get rid of that square root where it's at. You won't get rid of it completely, but here we want to rationalize this numerator. So the same way that we rationalize the denominator in algebra, we're going to rationalize the numerator. So we multiply. To do that, we multiply by the conjugate. So instead of square root of x minus 9, we're going to multiply by square root of x plus 9. What you do on the top, you have to do the same thing on the bottom. I am going to go ahead and multiply out that numerator, but I'm going to leave the denominator factored because our goal is to get this x minus 81, because if we plug in our x approaching 81, what we're seeing is that this is going to 0, and we cannot divide by 0. So we want to see if we can try to get rid of that x minus 81. So if we multiply this in the numerator, square root of x times square root of x is x, we'll get plus the square root, or plus 9 square roots of x, minus 9 square roots of x, and negative 9 plus 9 is negative 81. Now, when you're multiplying by conjugates, this should always happen. You should always get those middle terms to add to 0. All right, in the denominator, I'm not going to multiply it out because I want to try to get that x minus 81 to cancel out. And we see that it does. If I simplify that numerator, we get x minus 81 in the numerator, and then we have x minus 81 and the square root of x plus 9 in the denominator. We can divide top and bottom by x minus 81. If everything divides out, remember that leaves us with a 1. on that part of the fraction, and then we get 1 over the square root of x plus 9. And this one doesn't look a whole lot better than what we started with, but one major difference has occurred. And that is now when we plug in x equal 81, we do not get a 0 in the denominator. We get 1 over square root of 81 is 9 plus 9, we get 1 over 18. And that's something that would probably be a little hard to identify when you're looking at either a graph or even a table, because 1 over 18 is not a fraction that we're typically familiar with. All right, this last example, we've got the limit as x approaches 0 of a complex fraction. So that means we have fractions within the fraction. Our numerator is 1 over x plus 2 minus 1/2, and our denominator is x. So in algebra, when you have a complex fraction, the easiest way to get rid of it is to multiply by the least common denominator. So we're going to look at these three pieces here, the 1 over x plus 2, the 1 over 2, and the x as three fractions. So we're going to write that x as x over 1, and our LCD here, our least common denominator, is going to be x plus 2 times 1, or just 2 times x plus 2. We're going to multiply all of the pieces of our complex fraction by that LCD. And so if we multiply 1 over x plus 2 times that LCD, the x plus 2 is going to cancel, and we're going to just be left with a 2 for that first fraction. We get minus 1/2. So if 1/2 times that LCD, the 2 is going to cancel, but we'll have x plus 2 left. Make sure that you put parentheses around that or distribute that negative. Common mistakes there. And then in the denominator, nothing's going to cancel because we just have a 1 in the denominator. So we're going to get the 2 times the x plus 2. You can write them in any order. But again, just like we saw in the last example, our main goal, if we plug in x equals 0, we're going to get 0 over 0. And that 0 in the denominator, that 0 that we plug in for x, is our main thing. We want to try to get that x to divide out. So if we distribute that negative and combine like terms in the numerator, distributing that negative is going to give us a negative x and a negative 2. So when we combine like terms, we'll get a negative x, and then 2 minus 2 is 0. We still have our denominator. We haven't done anything to it, but now we have that common factor of x. So we can divide top and bottom by x, and our fraction simplifies to negative 1 over 2 times x plus 2. Now we've gotten rid of that singularity in the denominator, and we can plug in. So we get negative 1 over 2 times 0 plus 2, or negative 1/4. Now that would probably be something that you could recognize on a table, but probably not something you would recognize if you were looking at it on a graph. So that's why I like the analytic approach, because it's very easy to get to that answer if it's something that we can simplify that fraction. All right, I'll catch you guys next time.